Okay, this is section 5.4, part 2. In this video, we're going to talk about how we find those conditional probabilities intuitively, and then also what we do when we have a contingency table. And honestly, that's really a lot easier than it probably ends up being described in the interactive assignment, maybe, hopefully. And also just another example of using that and probability when we're dealing with independent events and we're looking at multiple draws or whatever. All right, so if we want to be able to find these conditional probabilities intuitively, then what we want to do to find the conditional probability of B given A, we're going to assume A has occurred and then calculate the probability that B will occur. So think back to what we said about independent back in this videos for section 5.3. We said, does the event or the whatever happens, does the outcome change my possibilities? So when I was flipping a coin or rolling a die, drawing things with replacement, everything got reset. I still had 6 sides on my die. I still have 2 sides on the coin. I still have the same number of marbles or cards or jelly beans or whatever I'm drawing. If I put them back, then everything's reset. But if not, what changed? So calculating that probability, knowing that A has already occurred. One thing you can think of is that conditional probability limits the world that we're looking at. Once we know A has happened, we're only really looking at events where B also happens for those outcomes. So if there's not a chance, so like if I want to know what's the probability of drawing a heart given I know I drew a red card in a standard deck of cards. Well, if I know I have a red card, then I already know that I have one of 26 cards. So I only have 26 cards that I'm looking at now. So what's the probability of me getting a heart given it's a red card? Well, that would be 13 out of 26, or 1/2. Instead of, what's the probability of getting a heart? Well, that's 1 out of 4. So there's our difference. All right, so an example with a contingency table. This is where that idea of kind of limiting what we're looking at really comes into play. So when we've got our contingency table, and of course here's our lovely males and females, and I think that I've decided it must be, you have to pick what's your favorite, cat or a dog. And because otherwise, I mean, I have both dogs and cats, so I wouldn't be able to be part of this table. We have to have things that are disjoint. But if I wanted to do conditional probability based on a contingency table, it really isn't difficult as long as you know the trick. And the cool thing about a trick in math is that once you see the trick, it becomes a tool and you can use it. It's not just a trick anymore. So here's what we want to make sure we do. So let's say that I want to find what's the probability of someone liking cats the best given they're female. Well, what this means, so this, remember that our wording, and this should have been in your, in the interactive assignment, being able to read this symbol, the symbols for this. That vertical line is usually read given. Or to use the conditional probability, what's the probability that someone likes cats the best under the condition that they are female. So once I know that, once I know this condition, and I'm going to highlight this in blue, very light blue. Let me use darker blue because that's not helpful. There we go. So under this condition, this means that I know that what I'm looking at are the females in the population or in the sample or whatever this is, this group of people. So I no longer care, for the sake of this probability question, about the males. I really only care about, of the females, what's the probability that they like cats? Well, that's going to be 39 people, or 39 females who like cats out of a total of 48 females. Those are the only numbers I'm going to look at. So I'm not doing, if you look at the formula, you see the formula in the interactive assignment, or especially, I hate when this comes up when you're doing the homework, because I don't want you trying to figure this out using a fraction, putting a formula over something else, and blah, blah, blah. This is so much easier. Just looking at, okay, so how many females like cats out of the total number of females? So we have 39 females who like cats. There's an E in there. Out of 48 females. Period. Done. That's got it. Now, this order matters. And I know it feels backwards, but it's not. So if you think about the way we're wording it, we're saying, what's the probability of this happening if this other thing has already happened? So the other thing that's already happened, that's what we've got to, that's what limits everything. That's what defines the group that we want to look at. So if I switch this around, what's the probability that someone is female if we know that their favorite is cats? Well, that's a different setup. And so let me pick a different color. Maybe purple. And so now I'm looking at cats. Given, I know they're cat lover. I know they think that cats are their favorite, or they say that cats are their favorite. So I know I'm looking at that column now. I've limited who I'm looking at. And now I can say, well, again, that 39 is still the important number. I have 39 females who like cats out of 49 people. Oh, these numbers are really close. I'm sorry, that's just crazy. About how close that is. I did not make this table up. I kind of wish I had, so that I could have made those numbers a little bit less similar. But there is a difference there. Hopefully you can tell where the numbers come from. So now I'm using this number as my bottom number. The total number of cat lovers, as opposed to dog lovers. And then, of course, still females who like cats. All right, so contingency tables, don't let those end up throwing you off. They're actually really easy to find probabilities in, as long as you know the trick to apply. All right, and so let's look at one more example where we're actually multiplying through, and we want to, maybe draw multiple cards. We want to know what's the probability of me getting. So here's our exploding snap deck again. Let's say I'm going to draw 3 cards. Draw 3 cards. This time I'm going to draw 3 cards without replacement. And there's some different things we could find. Maybe let's find what's the probability of getting 3 hearts. What's the probability of getting 3 stars? And what's the probability of getting 3 smileys? All right, so you might already be wondering if I made a mistake. I did not. This is intentional. So 3 hearts. Well, again, just like we saw before, as far as my hearts are concerned, I have 1, 2, 3. So 3 hearts means 3 cards, and each one of them is a heart. So when I think about finding that probability, I'm going to think of it as a heart and a heart and a heart. And I'm going to remember and means multiply. So I'm going to go ahead and put 1, 2, 3 sets of parentheses. And I'm going to go ahead and put my fraction bars because I know that's going to happen. And I'm going to look and I say, okay, I've got 3 hearts out of 12 cards. But I'm doing this without replacement. So if I draw a heart, if I don't draw a heart, then it's not one of the scenarios where this will work. So it doesn't matter. But if I do draw a heart, then I now have 2 hearts left out of 11 cards. And if I happen to get 2 hearts in a row, then I have 1 heart left out of 10 cards. And I just want to figure out what that probability will be. So in this case, if you aren't fraction phobic, then you might see that 3 times 2 is 6. 6 will go into 12 twice. And so I could reduce that down and end up with 1 over, I believe, 220. If you absolutely have no idea how I managed to do that, and you think that might have been some sort of witchcraft or similar, then don't worry about it. Just pull out your calculator, and you can put this in just like it says. So parenthesis 3 divided by 12. Of course, if you want to reduce that, you can, but there's no need to because your calculator will do the work for you. 2 divided by 11, new set of parentheses, 2 divided by 11. Close that set, open a new set of parentheses, 1 divided by 10. Close parentheses, hit equal, and we will get 0.0045 for that 4-5 repeats. And you may or may not remember this from, I don't know, maybe even elementary school. But when we have a repeating decimal, we draw a line over the part that repeats. That just allows us to keep the exact number. Of course, when you put this in the homework, you're going to put it in rounded. So that's just me liking to be precise because I'm a math person. All right, so that's our probability of getting 3 hearts. So basically, I would have to draw all 3 hearts when I draw those 3 cards. Now, if I want to find the probability of getting 3 stars when I draw 3 cards without replacement, well, I've got 1, 2, 3, 4, 5 stars. And so my probability is going to be a little bit different because I'm going to start with 5 out of 12. Of course, I know I'm drawing 3 cards. I know I'm going to be multiplying. We know we're going to drop 1 each time, so 5, 4, 3. Don't forget that we also need to drop the bottom number. I've had people do this, and they'll do the 5, 4, 3 on top, but then they'll keep it 12, 12, 12. So you got to be careful. This is going to be 12, then we'll drop to 11, then we'll drop to 10. All right, so in this case, again, if you want to do this by reducing fractions, you can, but 4 times 3 will give us 12. So that would just cancel out altogether. So that 4 times 3 would cancel out that 12. And then 5 goes into 10 twice. So I should end up with a 1 over 22. But again, don't freak out if you don't know how or why I did that or why I would want to do that when calculators are real and wonderful. So you can do parenthesis 5 divided by 12, close those parentheses, times a new set of parentheses 4 divided by 11, Close those parentheses, multiply again. New set of parentheses, 3 divided by 10. Type all that in. We're going to get 0.045. And again, that 45 is what repeats. Which hopefully makes sense because, look, we just have a difference of being a multiple of 10. So that decimal basically just moved over once. All right. And then last but not least, we have this question where we want to know what's the probability of getting 3 smileys. Well, now, if I was doing this with replacement, then this could happen. I could say 1 out of 12 raised to the 3rd power, because each time I look at the card, I put it back, shuffle again, and draw a new card. So I've reset. But since I'm not resetting, then you might just be able to say, hopefully, you could just look at that and say, well, that's impossible. And what's our probability for impossible? If something is impossible, the probability is 0. Now, and the other way that we could look at this is to say, okay, well, we've only got 1 smiley face. And so if I try to start out with 1 out of 12 and I start subtracting, there are no more smiley faces, but there are 11 cards. And then I'm going to draw something, but there are no more smiley faces out of 10 cards. Or really, I just kind of have to stop. But either way, I get 0 out of something. What is 11 times? Not that this bottom number matters, but just since we have it written out. But we get 0. There's no chance. There's no chance of getting 3 smileys because there aren't 3 smileys in there. So that's impossible. And that can happen, and we can notice it ahead of time and just say, that's impossible, not going to happen. Probability is 0. Or we can try to start working out and then say, oh, well, I don't have any smileys, so I have 0. And as soon as I have 0 in the numerator, I'm going to have a 0 probability.